In this video, we present a work drawing tiny networks, spotting expressivity bottlenecks, and fixing them optimally. In this work, we aim to reduce the computational cost of neural networks. If we look at how we train a neural network, we start with an architecture, here represented by the shape, and a choice of parameters, here represented by the color. Then, using gradient descent, we can optimize the parameters to minimize the loss function. However, if we want to optimize the architecture, we typically need to start with multiple architectures and train them. Then we will evaluate the performance of each architecture and select the best one. This trial and error process can be very costly. Hence, to reduce the cost, we propose to optimize both the parameter and the architecture in a single optimization process. To do so, we start with a small network and we grow it as we train it. To understand how we make neural network grow, we should first go back to the basics. In neural network training, on one side, we can change our prediction function in the subspace parameterized by the parameters theta of the network. On the other side, we have the loss function that tell us how well our prediction function is doing. The goal is for us to find the best parameters that minimize the loss function. To do this, we use the first order development of the loss function around the current parameters theta that indicates the impact of each direction on the loss. Using this information, we update theta in the opposite direction of the gradient. However, this only helps us to move the space parameterized by theta and does not help us to change the architecture of the network. To do so, we need to consider the derivative with respect to the function. This leads us to a similar first-order development, but this time in the space of the function. Now we know how to change our function. We first can look at what part of the change can be done by updating the current weight. To do so, we consider the tangent space to the space of parameterized functions at the current function. At first order, this is the space of function that can be reached with a single directional update of the weights. We then take the best possible direction in this space, which is exactly the orthogonal projection on the tangent space. However, if the network is not expressive enough, the difference between the desired direction and its projection is non-null. We call this residual the expressivity bottleneck. This direction then guides us in the extension of the network.
We will now explain how our theory applies to a feed-forward networks with two hidden layers. In the diagram, the blue squares represent the internal representation of the input. The column on the left shows the network's input, while the blue columns on the right represent the network's output. We denote the weight matrices of the first and second layers by θ1 and θ2. The first internal representation of the input x is y equals sigma θ1 x, where sigma is the activation function. The output of the network is then z equal θ2 y. In this example, we do not apply any activation function when computing the output z. As stated, we aim to reduce the expressivity bottleneck of the network by moving in the direction of the functional gradient, that is, minus the derivative of the loss according to z. Before modifying the network architecture, we can evaluate the optimal parameter update of θ2, which best aligns with this functional gradient. When updating the second layer's weight from θ2 to θ2 plus delta θ2, the network's output z change by delta z equal delta θ2 y. To find the optimal delta θ2, we minimize the distance between the functional gradient minus the derivative of the loss according to z, and the functional move induced by delta θ2, that is, delta θ2 y. This is equivalent to minimizing the norm on the top of the scale. After determining the optimal parameter update delta θ2, we remove the corresponding functional update from the functional gradient and evaluate how to add neurons to best align with this projected gradient. We introduce two green neurons in the hidden layer, denoting their finite weights by A and their finite weights by omega. By linearizing the activation function sigma, the functional update of the output z induced by this architectural change becomes A omega x. To determine the optimal pair A omega, we minimize the distance between the projected functional gradient minus the derivative of the loss according to z minus delta zeta to y, and the contribution from the new neurons, which is A omega x. This corresponds to minimizing the norm that is on the top of the scheme. We can prove that the optimal configuration for the new neurons can be computed in closed form depending only on delta zeta 2, x, y, and z. However we apply the method on two hidden layer networks, we can easily extend this method to multiple feed-forward layers by considering a subpart of the network where z represents an internal representation before an activation function. Starting from a feed-forward network with only a few neurons per layer, we can train the initial architecture, add neurons at different layers, and continue training. This process can be repeated, adding neurons and retraining, until the network's performance becomes satisfactory or its size reaches a predefined maximum capacity. One might wonder whether our growing network will achieve full expressivity on a given dataset D. In other words, will the loss reach zero when following the previous pipeline? Interestingly, we can demonstrate a convergence property to the global minimum by considering a modified version of our method, which we call completed tiny. In completed tiny, the addition of neuron is adjusted. When tiny is stuck and does not find any new neuron to add, because all possible improvements require to take nonlinearity into account, we consider random directions. Under this modified approach, and under technical assumption, we can prove that the loss on the training set will reach zero, and for this, the number of neurons to add is less than the size of the dataset. For more precision, and if you are curious about our methodology tiny, you can check the paper Growing Tiny Networks, Spotting Expressivity Bottlenecks and Fixing Them Optimally. And if you want to test the code, you can check the Git repo TinyPub.